All right. Well, it's time to start another fireside chat with the experts. Do another one of these Stump the Chumps. See if I can ask a question that might be a little bit harder this week for Dr. Bill and Dr. Glenn. We have again with us this week. Couple questions, some follow up from last week, so I'll go ahead and start with those. But we'll just see how many we can get through again this week, just like we did last week. Sound good?
Sounds like a plan.
All right, so the first question is, can you have a detector that has too high of a resolution? Is a higher resolution detector always better?
Not necessarily. It depends on the application. Depends on the power of the X-ray system. It depends on the sample. It's in some applications, too much resolution is actually a hindrance. If you have a standard you've been using, like a medical device manufacturer or maybe the military, you have a standard that you've been using for 20 years, right? Your manufacturing process is more or less written in stone, and all of a sudden you produce an X-ray system that has too much resolution. You're going to start seeing things that are insignificant but concerning to certain people. Maybe you're the end user, or and in a lot of cases, I've had some medical applications where I've supplied high resolution detectors, and the doctors were confused, and they actually rejected the product because it was too high of a resolution, right? That wasn't what the radiologists and the doctors were used to seeing. So that's the practical part as far as from a customer point of view. Then you have other concerns as far as detector size and detector grayscale, as well as the size of the pixels, right? And the ability to significantly light up or excite the scintillator and the diodes, photodiodes and flat panel detectors with an adequate amount of light. In our case, invisible photons. And in some cases, you'll need a much higher power. Then we get into the resolution side of the equation. Do you really need that much resolution to see the actual product, right? And as far as a lot of people will get pixel size and pixels and image size confused with pixel size and resolution as well. A larger detector may be 1.3 megapixel. The same size detector in 4x6 or a 3x4 or a 2x2 will have the same amount of pixels. So just because you're getting a larger detector doesn't always equate to a larger amount of pixels or a smaller, higher resolution system. Anything to add to that, Bill?
Yeah, I was chuckling earlier because I remember that. I don't know if you remember the casting customer we had. They had a really old film system. You could barely see voids and issues and cracks on those castings. And then we upgraded them with a digital system. And all of a sudden, all their samples failed. Remember? Like, something wrong with your X-ray machine. Now all our samples are failing. Like, oh yeah, now you can see what you're making. But you're right. I mean, there's a lot of resolution is a tough one because it's one of those things where you don't know what you ask for, right? And sometimes you end up seeing information that's really not valuable, and information that you don't use is noise, right? So you end up with a lot of noise in your information that don't really add anything to what you're trying to do. But what the other aspect you touched on, and I wanted to explore a little bit more, is that relationship between resolution and pixel size and spot size. And that's one of the things that it's kind of blended all together and people don't really understand. They look at, for example, a flat panel with 100 micron pixel and they say, oh, 100 micron pixel, that means that all best I'll be able to see from my sample is 100 microns, right? Which 100 microns is 4 mil, right? Which is a big feature. If you're talking about the microelectronics and some of these other applications, then a micron is a big feature. And what has to be taken into consideration is magnification, right? So if you have a feature, that 100 micron pixel is going to reflect 1 pixel on your sample if your sample is right on top of the sensor, right? Meaning that there's no one-to-one magnification. As soon as you move that sample closer to the source, away from the sensor, now that 100 micron feature on your sample can light 2 pixels on the sensor. And if you move closer to the source, now that 100 micron area on your sample can light 4, 8, 16, 32 pixels on the sample, on your sensor, right? So that's how we can get sub-micron resolution with 100 micron pixels, right? And that's something that sometimes gets confused out there, and X-ray companies don't make it easier, right? I think it's sometimes they like the confusion, so people just get, okay, I'll just buy it, and that's what we try to do, right? Try to explain the science and the technology behind it so people can make decisions with their eyes open. And then the other thing that gets confused all the time is, oh, I want the smaller pixel possible because that's going to give me the best image. Well, there are also trade-offs there. If you have a really, really tiny pixel, right? A really tiny pixel, remember that the amount of photons per square centimeter hitting your detector is not a function of the size of the pixel. It's a function of the source that's shining that sensor, right? So if you have 100 micron by 100 micron pixel, you might have a flux of X-ray photons hitting that area. Now, if you break that in half, so 50 micron by 50 micron pixels, so you have 4 pixels instead of 1 big pixel, the flux on each one of those is going to be proportionally reduced. That means that if you want the pixels to be as bright, you have to increase the flux of X-ray photons, which means you have to increase the power on the X-ray source. Or, like everything in life, or you increase the time that you're going to be collecting those photons, right? Which in X-ray lingo is increasing the exposure of your sensor. What does it happen? Your image is going to get slower, right? So you can't have it all, right? I had an old professor that called nature the short blanket, right? You cover your feet, you expose your face, you cover your face, you expose your feet. You can't have it all. You're going to have a compromise. So smaller pixels, you can get higher resolution, but your image is going to get darker. So I'd increase the power of the X-ray source, which is going to, like we talked last week, increasing the power of the X-ray source means that you're going to get more thermal noise, which is going to increase the size of the target, which is going to reduce the resolution, which is what you don't want. Or you increase the size, the exposure on the sensor, which makes everything slower, which no one likes. Some applications that do require high resolution no matter what, medical applications, some casting applications, some industrial applications, they just live with a very long exposure time, right? You get to high resolution, but it takes 30 seconds. It takes a minute to collect an image. That's why, because you keep tiny pixels and you just keep collecting those photons. And you collect, and to the point where you think you have a good image. There's also some considerations from the speed of the sensor as you start shrinking the size of the pixel, right? How much of the electronics you're going to keep inside each pixel. And because if you shrink enough, the electronics won't fit inside the pixel itself, which means you have to bring, for example, with the A to D analog to digital converter, won't no longer fit inside the pixel size itself. Now you have to bus the analog signal down, have the ADC outside on the sensor, and then that means that you now have to have a pipeline of analog signals, and that gets more complicated. You have some more noise associated. So there's a lot of trade-offs that that come into consideration when talking about resolution, speed, and the power of your X-ray source. So at this point, I don't remember what the question was anymore, but I think I answered it at some point there.
Right. But another consideration that rarely we hear from an end user, they'll look for pixel size, they'll look for detector size, but one of the deciding factors on resolution as well is the scintillating material and the scintillating screen.
Yeah.
Right. So that will affect your overall grayscale values, and it affects the perceived resolution. Right. So it's a complicated number, and you know, what we'll do is we'll query the customer and try to find the right combination. And it's not necessarily super megapixel. It could be a fairly benign number of pixels, but with a really fast or small grain scintillator, right? And for people that don't understand, the scintillator is essentially required in all X-ray applications because we have to convert invisible photons, visible light, for lack of a better term there, to visible light or electrons.
Yeah.
And actually, the scintillating screen is the ability to convert that. Essentially, we excite a phosphorescent type material, and depending on the size of the grains of that material, we can change the speeds of the scintillator. Back in the old days when we were doing film, we would use different cassettes with the film placed inside, and you would use phosphor screens of different speeds and grain size to increase the light being exposed to the film. So instead of taking a 3-minute exposure, you could take a 1-minute exposure because and in some cases in film applications that would you would actually use lead as a scintillating screen if you had enough power in your X-ray source. Mm-hmm. So scintillators are a huge, a portion of that resolution that most people don't realize or even understand. So that's where our expertise comes in when we say, this is the best detector for your application based on many values.
Yeah, so and that's it's actually a pretty good point that we don't talk very often. And that screen, that scintillator layer that sits on top of the sensor, that defines how many visible photons are going to be generated by the screen that's going to shine the CMOS or whatever other technology you have for your sensor as a function of one X-ray photon that hits it, right? So let's say a low efficiency scintillator for each X-ray photon emits one visible photon. For a high efficiency scintillator for one X-ray photon emits 10 visible photons. So that means is that with a sensitive screen, with a sensitive, very sensitive scintillator, you don't need as much radiation to produce the same image, right? So you can run the X-ray source at a lower power. That also means that you can, that you're going to be able to see features on the sample that you might not be able to see with a lower sensitivity scintillator, because those few photons that actually show up on the sensor after they go through the source of your sample are not able to excite enough to produce an image. So there are nowadays there are two main scintillators that are used, Gadox and cesium iodide. And cesium iodide is a higher sensitivity scintillator. Gadox is a little bit lower. And for a lot of applications, it doesn't matter, right? Which one you use. You're not looking for that extra level of grayscale to make a decision in your application. But for some applications, that's what's going to define success or failure. And that's why, you got to talk to people like us to figure it out, right? Because you don't want to overpay when you don't have to. At least I don't like to overpay when I don't have to. Right? It's a thing I have,
I think a lot of people have that one.
Yeah, I think it's kind of a universal thing.
People are funny that way.
That way, yeah.
That brings us to another, I know it's kind of a long question or a long answer to a question is, what's the resolution of my X-ray system? How do you determine the resolution of the system as a whole? We've talked about focal spot size. We've talked about pixel pitch, resolution of a detector. A lot of times we'll see in spec sheets on systems saying, you know, the resolution of the system is this, and give a black and white number. It's very clear. So how is that determined, and what's your feeling on that?
It's never a black and white number. All right. You can create a number, but it's never black and white. As we were talking about detector resolution, we have X-ray tube resolution. We have magnification. We have how close the sample is to the X-ray source. A smaller focal spot will enable you to get more magnification by getting closer to the source. You know, we do numbers. We do have image quality indicators of various types. And with that, the same as with the detector, you have two different types of resolution there as well. You have contrast resolution, and you have the ability to have geometrical resolution, right? A physical resolution of the X-ray tube, kind of a set point, a line in the sand that says, this is your minimum resolution. And then we have system magnification, which increases the resolution or perceived resolution, right? So if you think of it as a microscope, just because you look through a microscope, you haven't really increased the resolution of your eyes, right? All you've done is magnified what you're looking at. So that's the same concept with system magnification, right? And the system magnification includes the size of the monitor. If we have a 60-inch monitor versus a 10-inch monitor, you're going to get a lot bigger image to view, right? Your defects or your artifacts or your landmarks are going to be huge compared to a smaller monitor. So there are a couple different versions of you know, resolution and how you achieve that. Just know that all manufacturers, as a de facto, will give you a resolution number based on the maximum magnification of the machine, right? If we use the point of contact resolution numbers, it would be just like looking at a, you know, a small item with your eyes. You wouldn't actually be able to pick out details. So that number would be quite small, like somewhere 4, 5, 6 line pairs per millimeter, which is one of the indicators that we use to judge the overall resolution and, you know, magnification of an X-ray system. So it's you know, again, like Bill said, you know, it's a short blanket. There's not a lot of there's the compromises. X-ray in general is a general rule. Building an X-ray system is a compromise. Everything you do is a compromise. Your magnification's a compromise. Your resolution's a compromise. The amount of power that you're producing in the X-ray tube is a compromise. You know, everything is a compromise. So you actually have to pick the best of all of the means available, right? One thing, since we're talking about maximum magnification, gives you the maximum perceived resolution, right? A short source to image distance, like a benchtop X-ray system, it's going to be limited on your geometrical magnification. So we may be depending on some system magnification in there to actually give you, say, 50, 60 line pairs per millimeter, right? Which is what we would consider a high resolution X-ray system. Back in the day, 30, 40 line pairs were pretty decent. One of the problems with the line pairs per millimeter is they were designed back in the day, back in the 50s, early 60s, and they only go up to 20 line pairs per millimeter, all right? So that's, again, another compromise. So to eliminate that, we do some tricks with the line pair gauge to actually reduce those distances between the lines to give us the ability to measure up to 40 and 60 line pairs per millimeter. So it's, you know, resolution is, and magnification are key, especially in microelectronics. In resolution wise, if you're looking at larger focal spots, you can increase the perceived resolution by having higher magnification, but you can also open up your source to image distance, right? Medical X-ray systems use a 3,000 micron focal spot, which is huge, 3 millimeters. They do that because they have to get a lot of power, and they have to do it very quickly in between breaths for the most part, right? So what they'll do is the standard distance for source to image distance on a medical X-ray system is 36 inches. And they can go up to 48 inches. And in industrial applications, they may run a source to image distance out to 96 inches or so. And the reason for that is they'll get the best resolution out of the X-ray tube and out of the detector by opening up that source to image distance and essentially just using the sweet spot right in the center of that X-ray beam, which is essentially what we do with a microfocus X-ray source in the 5 micron range with high magnification. We're using the perfectly aligned photons. We're not dealing with any of the penumbra or scatter or some of the other things that would affect resolution and affect that ability to measure that number.
Yeah, that's the other thing that, when you look at those, like David was saying, the black and white. I mean, the new Ford Mustang GT 500 claims 0 to 60 miles an hour in 3.3 seconds. Now, do you think if I buy one, I'm going to get 3.3 seconds if I try? Yeah, right? That's a special track with a special driver with special tires, and right? And that's what X-ray companies do, like everyone does, right? You do your special, the best, with experts running, and then, I'm not lying. If you do all that, you can get those results, right? But the point number one is, do you need a GT 500 to go to Costco on a weekend? You don't, right? And at the end of the day, and that's something that we've been doing since we started the company, is we got to do what's right for your sample in your company, right? You don't have to spend $70,000 on a car to carry groceries that actually the trunk is like this big, right? And we end up overpaying for something you don't need, and you end up not getting the things that you actually need. So looking at specs and just doing a spreadsheet type of comparison of machines is very dangerous, because you might end up cornering yourself on a hole and buying the wrong stuff. And that happens all the time, right? It happens all the time. They, customers, if you're not careful, you can just buy in the, some companies marketing BS. And like, oh yeah, I really need that. Oh, that's the greatest new thing. And you end up overspending for something you're not going to use, right? And the stuff that you really needed gets neglected. So instead of upfront talking about resolution, because resolution, like Glenn said, right? Line pair gauge. You know what a line pair gauge is? Is a really thin film with gold-plated lines, right? That's, for an X-ray system, it's the best case scenario to produce an image. A really dense line, gold-plated, very heavy material, metal, against a really thin background, right? I mean, how often do we have an application or customer with that? It doesn't exist. So what happens as soon as you have mass and you have to go through different metals and different epoxies, etc., well, you end up having to crank up the power on your tube and your resolution lowers. That's just physics. There's nothing we can do about it. So you think you're getting that resolution, you're not going to get it, because that was done like the GT 500 in a special track with a special driver with a special tires, perfect condition, right? Sunshine, perfect humidity on the track, and you get that number. Yes, you do. But does it matter to you? So that's what the conversation about resolution, that's what we have to get to, is what really matters, right? So you don't, you don't try to spend tons of money on a nano-focus source that never going to get nano-focus resolution. First, you never needed it. And second, because the power out of the source, by the time it's out, it's not in a focus anymore. So the bottom line is resolution on those data sheets are based on ideal conditions and should be taken with not a grain of salt, like a bucket of salt.
Right. The perfect storm for destroying your resolution is a aluminum wire or a bond wire under a stainless steel heat sink.
There you go. Yeah.
It doesn't matter what your resolution is, you're not going to be able to image it. And the basic reason is when you shoot through that stainless steel, it's going to cause all kinds of X-ray scatter. It's going to essentially deflect those photons, and you're not going to get a pristine image no matter what you do.
Or even talking about a simple PCB, right? A simple PCB nowadays, even the simplest ones have multiple layers, and you can have a power layer, ground layer made of copper. As soon as you start putting those metals, you have scatter, right?
Right.
And there goes your resolution. So
right.
you're going through a standard PCB, you're going to have, again, unless you're looking at a line pair gauge, everything else is going to get worse, right?
Right. Right.
So beware, people.
Practically, I think the best thing to do is basically take a look at what you want to look at, right?
Yeah, best thing.
If you inspect cell phones, then let's X-ray the cell phone and see, can you see what you need to see? Right?
Exactly.
Well, that's always the bottom line. And then that's the most beneficial question you can ask yourself if you're buying an X-ray system. Can I see what I need to see? Specs don't really matter. It doesn't matter if I have the highest resolution X-ray tube or even the highest resolution detector. Can I see what I need to see? That's the simple question. And then everything else is based off that. It's all the specifications would be based off that simple answer of yes or no. So.
Right, or if you're using algorithms to analyze it, or we're using our AI to analyze it for you, can that see what you need to see?
Exactly.
Maybe it doesn't look pretty to you in our eye, but the computer is like, oh yeah, that's good, that's bad, it's obvious to me.
But even simpler stuff. I mean, we've had customers who bought machines and then realized that the samples don't fit. Like, well,
yeah, that's true.
If you're inspecting a 48-inch board and you buy a 50-inch machine, there's a chance that, but it fits. Yeah, it fits, but it doesn't move, right? It's just stuck in there. And once you put it in, it doesn't come out. So it's, I think the danger in this, and we've seen this from time to time, some companies try to focus the customer on one specific aspect of the machine, right? Resolution, and then corner you in that aspect and tell you that's the most important thing. Don't think of anything else. And when you buy capital equipment, you buy a machine to inspect a wide range of product that most of our customers do, you got to be more holistic, right? Yes, some of these things are very important, but the overall package, if you can move your boards in and out or your samples in and out of the machine as fast as you need, integration of the machine to your ERP or MRP, all these different things that play a role. Support, right, afterwards. After you buy a machine, things break, things change in your manufacturing, in your processing. So are you going to have someone who can help? So it's a much broader choice that you have to make. And if you have, it's interesting. So if one company is focusing you in one aspect only, it's suspicious, right? There's probably something else missing. They don't want to tell you.
Right. Because keep in mind, everything with X-ray is a compromise.
Yeah.
Right.
All right. Well, thank you, gentlemen. Appreciate the time.
Half an hour already? That's
half an hour already. Answered 2 questions that were, aspects of one overall question. But anyways.
Well, at this pace, we're going to be done in 25 years, I guess, huh?
Yeah, roughly. Especially if people keep adding to the list. So,
Well, keep the questions coming, right? You don't want to stop people from doing that.
Yeah, definitely. So if any other follow-up questions came up, please definitely let us know. If you're watching this on YouTube, comment below. And we'll be doing this again next week. So we've got a list of questions to ask and get through. So thank you, Glenn. Appreciate your time.
Thanks, man.
Thanks, Bill. Appreciate it.
Thanks for joining us.
Quay, which one?